Hello, my name is Nesnianowski, and so we're going through monoidal category theory, and we're doing the first real section of this book. Okay, and as I explained in the beginning, the book starts with an introduction to category theory, but even before we do categories, I will not mention the word category. Well, I will mention it, whatever. This time I won't mention the word category, but what we're going to do today is just talk about sets and functions between sets, okay? And what we're going to do is we're going to get a lot of different intuitions about categories by looking at this. So one of the main ideas of category is that it's not the object or another object that's important, but really it's the morphisms that are important. Okay, and what we're going to do today is we're going to show this idea, again, without talking about categories, but just talking about, instead of just talking about sets, we're going to talk about sets and morphisms between sets. So you're going to have a set S, and you're going to have a function f from S to t. And we're going to see a lot about these functions and what they do and how they compose and stuff like that. We're just going to talk about sets and how they work, okay? And the main goal here is to get you an intuition of this morphism, this arrows between objects, how they define and describe many different phenomenon, not only in sets, we're going to talk about sets, but then later on we're going to see some of the ideas here that we learned today are going to show up over and over and over. And I'm going to constantly, throughout the book, say, or throughout all these lecture series, go back to section 1.4 where we saw this and this about sets. Well, now let's generalize it and talk about something else, okay? So the ideas here are extremely important. And I assume a lot of you know about sets and stuff like that, but we want to get into it. Okay, so let's start at the beginning. So we know what a set is. A set is a collection of objects. It's a collection of things, and you write, usually something like this. S is A, B, C, or something like that. That means S has the 3 element sets. We're going to talk about sets of shirts. We're going to talk about sets of pants. We're going to talk about sets of numbers. We're going to talk about sets of students in a class. We're going to talk about lots of different sets. But we write them like that, and we have 2 notation. If you have X an element and X is in the set, we write that. That's a funny E. And if X is an element and it's not in the set, okay, if it's not, if X is not in the set, we cross it out like that. So we're going to do that over and over again. That's just about notation. Let's just talk a little bit more about other notation. We have lots of different sets of numbers. So we have the set of natural numbers. 2, 3, dot, dot, dot. We have positive and negative numbers. These are, again, different sets that we're going to see throughout the text. -3, -2, -1, 0, 1, 2, 3. Okay. We're going to have the set Q of rational numbers. Those are whole numbers such that M and N is a member of Z, and N is not, M is not 0. So these are rational numbers, and okay, and besides that, we're going to have real numbers. Okay, and that's something that's drawn on the first day of class in 9th grade. You have all the real numbers. We're going to spend a lot of time in later chapters talking about complex numbers. Okay, so these are just 1, 2, 3, 4, 5 sets that we're going to see a lot of. All of these are infinite sets, and we have that. Okay? Okay. I'm going to need all the board space I need. So this is the first mini course that we have, and we're talking about sets and categorical thinking. Categorical thinking is this idea that we look at things from the morphism point of view, not just the objects, the sets, but we look at it from the functions between sets ideas. Okay, great. Okay. Okay, great. Next. Okay, so there's lots of different operations we can do with sets, okay? And so let's just talk about 3 of them, okay? The first operation is called the Cartesian product. Okay, and what's that? Given a set A with a bunch of elements and a set B with a bunch of elements, you could talk about the Cartesian product of that. Okay, and what's this? These are pairs of ordered pairs of elements, A comma B, such that A is an element of A and B is an element of B. Okay, so in the book, I talk about A is a set of shirts and B is the set of pants, and ordered pairs of those would be one set and one shirt and one pair of pants. Okay, it would be the listing of all of these things. Okay, you can have A is a set of students in a college, B is a set of classes in a college, and then you can have for every student in every class, there would be an ordered pair of them. There's a little discussion about this notation in the book. You should definitely read it. It's going to be kind of important. Okay, you can have the set of boys in the class, the set of girls in the class, and then you can have every single possible pair, you can have that. Great. First rule about the Cartesian product is if you have 2 sets, and you want to know the number of elements in the set of the pairs, well, it's the number of elements in A times the number of elements in the B. So let's say you have 5 boys and 7 girls, then the number of pairs, the possible pairings that you can have is 5 times 7 is 35. Okay, so that's a simple rule. Now, you can generalize the Cartesian product not to 2 sets, but you can have n sets. So you can have S1 cross S2 cross S3 cross ... cross Sn. Okay, so you have n different subsets, and then you can talk about not ordered pairs like we have here, but ordered n tuples. Okay, and ordered n tuples, so a typical element would be something like this: S1, comma, S2, comma, S3, comma, Sn. That would be a typical element, would be ordered, so that's a round bracket is like that, ordered, and each one of these, S1 is a member of this set, S2 is a member of this set, S3 is a member of this set, etc. Okay, and now we can ask also the same question about how many elements are in the ordered pairs, and the answer is, okay, it's the number of elements in S1 times the number of elements in S2 times the number of elements in S3 times ... times the number of elements in Sn. Okay, and again, if you have 3 shirts and 4 pair of pants, then you have 3 times 4, you have 12 elements in the ordered pair. If you have 3 shirts, 4 pair of pants, and 7 hats, then you have 3 times 4 times 7 number of outfits. If you include all 3 of those things are a set. Okay, so this is a nice operation. We're going to see this operation very often. The Cartesian product, named after Descartes. Next, 2. The union of 2 sets. So given 2 sets, S and T, you can take the union, and basically that's those things that are in here or in here. It's the union, the combined sets. So the set of students in one class, union the set of students in another class. However, there could be, one student could be in both classes, and that doesn't bother us. So this is a typical thing. So, for example, we're talking about outfit. We're talking about, if S is the set of shirts and T is the set of pants, then S union T is the set of clothes that you have, or something like that. Okay. A third operation, which might be a little bit less well known, is called disjoint union. Okay, and it's written a certain way: S disjoint T. Okay, it's kind of like U, but it's not, and it's separated. The idea is as follows. Sometimes, if you take two sets, you're not interested in just the union, you're interested in, because it might be that the union has common elements. So for example, I have S as a set of students in one class, I have T as a set of students in the other class, but there could be some students that are registered in both, okay? So I would only count them once in this set, okay? As opposed to that, if S is the set of shirts and T is the set of pants, well, I wouldn't count them together. The same thing, because I mean their union is the disjoint union. Their union is each one, not there's no overlap. There's nothing that's both a pants and a shirt. I guess some type of onesie or something, but I'm not sure we want to talk about that. Okay, so that's the disjoint union. So the disjoint union is the set of those elements in S or those elements in T. Now, I have to somehow distinguish them if there is overlap. So for example, let's go back to that classes. The set of students in this class or the set of students in that class, okay, the union, but I want to count those in this class different from those in this class. So there's a nice, cute way of doing it. Okay, there's a few ways of doing it, but let's do it this way. You might do it as follows. You might think of it as follows. S cross 0. Now, before we go on, that's a funny thing. What is this? These are ordered pairs where the first element is an S and the second element is 0. Not in 0, in is 0. So this has S number of elements, and basically what it is this is a bunch of S comma zeros. Okay, great. So we kind of tagging every element of S with a 0. Now you might take that with a union of T cross 1. Okay, I'm going to put parentheses here so that people can make the difference. T cross 1 is a bunch of ordered pairs where this is T and this is a 1. Okay, now we take the union of those two sets. So these are elements with S tagged on with a special thing that says, oh, you also have a 0 in it. And these are elements in T, and they're tagged on with a 1 on it, a 0 with it. And now these are elements of T with an extra 1 on it. Okay, and now the union of those is the disjoint union. In other words, it's a way of thinking of the disjoint union as two separate things, because even if there's some element that's both in S and in T, we're going to think of them as separate because this element here is going to be tagged with a 0, and this element here is going to be tagged with a 1. Okay, so we have that. Okay? And there's a nice little way of seeing that in terms of number of elements. The number of elements in S union T, in S disjoint union T is equal to the number of elements in S plus the number of elements in T. Okay, that's not true for this. Okay, let's talk about, I have a bunch of students from one class, I have a bunch of students from another class. What I will do is, in the union, the number of students counted in both will be, the overlap won't be counted, okay? Well, what I'm trying to say is, let's look at a Venn diagram, okay? This is the number of students in S, union T, so this is the number of students in S, okay? It's not going to equal to the number of students in S plus the number of students in T. In fact, this will be less than that. So it won't be equal, but they will be less than, okay? Because this is the number of students in S, this is the number of students in T. I'm counting the overlap twice. Okay, great. There's more discussion in the book, but that's fine, okay? So we're going to talk about these three operations on sets, but you know what? Our central goal in this section is not talking about sets. Rather, our central goal is to talk about functions between sets. So let's talk about functions. Okay, so if you have a set S and you have a set T, you could talk about F from set S to T, and that's what we're going to talk about. We're going to write it like that. Sometimes we're going to write it like this. Okay, Now, again, formal definitions in the book, but I just want to give you the intuition. What's it all about? A function is something that assigns to everything here something here. Okay? To everything here, one thing here. So it's a way of assigning, of giving over to everything's here, something here. And so we write it as follows. F of little s, that's a guy in here, is going to equal to little t. Okay? And so you can also think of it as a type of Venn diagram. Here's your S, here's your T, here's your little s over here, here's your f of little s over here. And so we can write the function like this. S goes to f of s. Okay? So we write it as follows, f of s. Another way to write it is as follows. A function is written with a straight line. Okay, but we can say it like this also, and we're going to use this notation throughout the book. Little s goes to little t over there. So with this little tail, this says this is a set, this is a set, there's a function from this set to this set, and that's fine. This is little s, an element in there, little t, an element in there, and there's a function like that. And this element goes to this thing. So you have to get this distinction between these two notations. This is from a set to a set. This is from an element in this set to an element in this set. Okay. Okay, good. Now, something else that's very important. Okay, for every set, there is a silly little set. There's a silly little function from S to S called identity on S. Okay, and this is the funniest, well, it's like I said, it's a silly function. Basically, identity on S of little s, so the input is little s, and the output is little s. It's a stupid function that whatever the input is, the output is. Okay, but we're going to use this function a lot. Okay, so that's the identity function. If you want to use it in this notation, it's little s goes to, maps to little s. Okay, that takes care of that. Okay, so that's what a function is. We're going to see more things about functions this entire video, but what I said was the important things about functions is you can get a lot of knowledge about sets by looking at the functions between them. Okay, so this is the central idea of this is the central idea of categorical thinking. Okay, so let's do the following. Here's a silly little set. It contains one element, the asterisk. Okay, I could have said the one element A, one element B, one element Jack, whatever you want. Okay, here's a set S, and we can look about functions like this. Okay, so we can write it like this. F from the one element set to the set S. So this is an interesting, I'm sorry, there might be a lot of different sets. S can't be empty, but there might be a lot of different functions like this, but then we talk about this. F of star, asterisk, is equal to little s. Okay? So what this function does is it chooses an element of S. Okay, so let's do a real live example. You have S is equal to the set A, comma B, comma C. Okay, and I want to talk about different functions. So one function like this would be something like this. F of star equals B. That's one function. There might be another function which we can write like this. G goes from star to S, okay? And so we have G of star equals C. And you might have another function, H, and H, which come and goes from the same place, is equal to A. Okay? So here's three different functions from star to S, okay? And the three different functions choose, okay, three different things, A, B, and C. Okay? Main idea is that such functions from a one element set pick out an element in S. Okay? Good. Okay. The book has a little more about notation. So for example, I might call F, I might call it little b. Okay? This is a little function from star to S. It picks out a little b. Okay, fine. Great. That's a one-element set. You might also be interested in two-element sets. Okay? So a function from the set, let's say AB, that's a nice two-element set, okay, 2S, it picks out two things in here. Now, it could be it's the same thing, so I shouldn't say two. It picks out at most two things here. Okay, so you might have f of A, and another element is f of B. And again, I'm not saying that they're different, but it could be two different things. So here's a set that picks out two different things. We could generalize this. We could talk about f from 1, 2, 3 to n. This is a function from an n-element set to S. Okay? And what this does is picks out n elements. So, for example, okay, here's S is the set of United States citizens, and you have F, which has, this set has, let's say, 330 million people, and you have S from 1 to 50, okay, and what this function might do is there are 50 states in the Union, and it might pick out the governors of each one of those states. So that's fine. Okay? Good. Okay. Okay. Okay, so what I showed you was that if you're going to talk about sets, you have to talk about elements within the set, and functions are good at describing the elements in the set. Let me talk about other aspects of sets. You could talk about T, a subset of S. Okay? Here's a set T and a set S, and there's a subset of it. T is a subset. So for example, you might have all the students in the class, you might have all the girls in the class. Okay, and every girl is an element of the thing. Okay, so a subset, and again the formal definitions in the book is T is a subset of S if every element of here is an element in there. Okay, and we also talk about T. So this is called a subset. This is the notation that we use for a subset, and we also could talk about this. T. This means it could be equal. If I cross it out, it would be T is a proper subset of S. It means it's really smaller. It can't be equal. So if if T is the set of all girls in the class, well, if the class consists of only girls, then this set is actually equal. But if there's a boy in the class, then the set of girls is not equal to the set of all students because there might be boys. So this is called a proper subset. Okay, and we can describe subsets also with functions as follows. T S, we might write it as follows. INC for inclusion of T into S, and because it's a subset, we make this funny little loop on the thing, and it's just a way of showing like this, that T is kind of inside of S. So, and again, if this is a subset of this, then every element here is an element here, and so the inclusion function takes the element in here to the element that it's in there. So again, if you think of these are all the girls in the class, and this is all the whole class, then the inclusion function takes a typical girl to the girl in the class. So inclusion of Jill, okay, equals Jill. Okay, so that's a typical type of thing. Okay, so the inclusion function is one type of one function that can explain, that can describe a subset. But I want to show you another one that's even more important than this, and this is called a characteristic function. Characteristic function. Okay, and the idea is as follows. If T is a subset of S, okay, then there's a function. I gotta remember how the goes. This is a Greek letter chi of T. Okay, so it's a Greek letter chi or chi, depending on what you want to do, and it has a subset T. It has a subscript T, and this is a function that goes from S to an interesting set, 0, 1. Okay, and 0, 1 is just a 2 set, and you might think of it as follows. The characteristic function of T on S is equal to one of two things, 0, 1. It's equal to 1 if S is a member of T, and it's equal to 0 if S is not a member of T. So the characteristic function describes what's in what's in the subset and what's not in the subset. Let's say that again. The characteristic function of T describes what's in the subset T and what's not in the subset T. If you want, you can think of it like this. Here is S, here is T, here's the set 0 and 1. Everything in T goes to 1, everything else goes to 0. Okay? Not a perfect drawing, but still very nice. Okay? Okay. The way to think of this is as follows. This function, this characteristic function, splits those things splits the set S into two parts. Those things that are in those things that are in T, those things that are not in T. Okay? So this function to two elements splits it into two things. Okay? Just want to contrast this. A function from this into this doesn't split anything, okay? This is a silly function because there's no choice. Every single element here must go to the star. So we'll call this like this. This means it's unique, and what it says is the unique of little s, well, there's nothing else for it to belong to. Here, you can belong to 0 or you can belong to 1. Here, there's nothing else to belong to, and so this is equal to star. Okay, so little s goes to star. Now, this is so unique. This is such a strict function that there's only one such function. For every function, for every set S, there's only one function going to a one-element set. By the way, I could have done this with another one-element set. That's another one-element set. And again, there's only one function. So we write this uniqueness, we write this with the exponential, with this one with a dot under it. Okay, so let's go through this again. You ready? This does not split the set into two. This splits the set into two. Okay? What else can we do? Okay? Well, we don't have to just split the set into two. We can split the set into three. So let's look at functions like this. Now let's think of a nice three-element set that we can split into. We'll call it, how about this? X, Y, and Z. So here's a function like this, basically takes S and splits it into three different sets. Those things going to X, those things going to Y, those things going to Z. Okay? Let's do another thing. Here, we can have, here's another set from 0 to 4. This is in the book, I think. Okay, from 0 to 4. This is the set of students, and for every student, you have a GPA, a grade point average. Okay, GPA. Okay, and what's the GPA? It's some real number between 0 and 4. Okay, so that's it. So this is, again, you're not really splitting the set, but you're to every element here, you're assigning some real number like that, and so it chops up the set in some way. This chops up the set into 3 things, and of course you can chop the set up into n things, whatever you want. Okay, we're going to see more about functions from one set to another, but I just want to give you a general important categorical idea, okay? And the important categorical idea is as follows. Well, let me say it in terms of sets, okay? Many times, given a set S, many times we're going to characterize the set, we're going to describe properties of the set by looking at other sets, let's say A, and looking at maps into it and saying, what do we have? So if we looked at a 1-element set, we have things like that. And if we looked at a 2-element sets, we can look at 3-element sets, we can do lots of things by looking at maps from the other sets, could be A, could be B, etc., like that, and we can look at maps into it. Other things we could do also to find out properties of S is look at maps from S to other sets. So we looked at a single element set, that's not too helpful, but a double element set and other types of sets we can also look at. So what we're going to do today, what we did today and what we'll do many times is we're going to look, in order to find out properties of these things, we're going to look at things mapping into it, we're going to look at things mapping out of it. And we're going to find out a lot of different properties. That's very nice about sets, but let me just make a general statement about categories. Given an element A in a category, we're going to find out lots of properties of this element A by looking at maps from certain specific sets into it, okay? And we're going to find out a lot of properties about A by looking at certain set C and maps from A to C. So we're going to both find out properties from maps going into A. We're going to find out properties about A by looking at maps, special types of maps going into A. We're going to find out special properties about A by looking at maps from A to other objects in a category. And this is going to be a main theme that we have. Okay. Okay, next, some more ideas about set. There is a special set called the empty set. There is only one empty set. It's a very interesting thought. There's only one empty set. The set has no elements whatsoever. Okay, and we're going to talk about, for every set S, there is a unique element, a unique function from here to here. Again, I'm going to write the uniqueness with this exponentiation point. Okay? Okay, so how does this function do? Well, it takes whatever's here, it takes an object in here into here. Well, which object in here does it take? Well, there is nothing here to take. And so there's always a map like that. It's somewhat conventional. There's always a map from here to here. And there's a unique map like that. Okay. By the way, we saw 5 minutes ago that for every element, there's a unique map from here. So this is interesting. For every set, there's a unique map from here to here. From every set, there's a unique map from here to here. Let me just foreshadow. we're going to say this is an initial object, this is a terminal object. Whenever you have such a property, this is when there's a unit for every element, for every set, there's a unique map like that. Okay, in the category, we'll talk about that. That's called an initial object, that's called a terminal object. We'll get to that. Okay, great. Next. Okay, next. Taking a set S, okay, then there's another set called the power set of S. Okay, let me tell you what it is. So let's first write out what it is. Power set, okay, of S, okay, and it's equal to the set of all subsets of S. Okay, so let's look at a little example, okay, and we have as follows. So the power set of the set A comma B is going to equal to, let's see, what subsets do we have of A comma B? Well, one of the subsets we have is the empty set, because the empty set is inside every set. Everything in here is in here, so it's in there. Next, the set that just contains A. Next, the set that just contains B. Next, the set that contains A comma B. Okay, so the power set is the set of subsets. So that's why this is in curly brackets, it's a set. Let's just do, for fun, let's do the power set of A comma B comma C. Here's a 3-element set, okay, and we get as follows. The empty set's in there, the set containing A is in there, the set containing B is in there, the set containing AB is in there. Okay, but don't forget C. Oh, the set, whoops. Okay, so I'm not finished my list, well, my set. The set that just contains C is there. The set that contains A and C is there. The set that contains B and C is there. And the set that contains A, B, C is in there. Okay, so, okay, let's look at the power set of A. Power set of A, oops, this is the set, the empty set, because the empty set's in every set, and the set A. Okay? Now we have a pattern here. The set with one element has, the power set of one element has 2 elements. The power set of 2 elements has 1, 2, 3, 4 elements. The power set of 3 elements has 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 2, 4, 8. Okay, if I did the power set of 4 elements, basically I would get these sets, let's say A, B, C, and D, I would get these sets, and then I would get another set, and then another, so that would be 8 elements, and then another whole set with every single thing in here, but with a D plugged in. So look what I did here, okay? I have 4 elements here, and then I wanted to look at what happens if I add a C. So I took the 4 elements here, and I put it over here. I took the 4 elements here, and I put it over here. And then what I did was I took the element C, and I added it into every set. So the empty set with C is just C. The set A with C is just AC. The set B with C is just BC. The set AB with C is that. Okay. 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 It's just keeping up with the power set. You might say that the power set is whoops. The power set of S is just the set of maps from this. So that is a subset. If you want all the subsets, you have to look at all the functions from here to here. Okay, and we're going to write that as follows. Hom, and I'll explain to you what that is in a while, of 0, 1. set of functions from S to the set 0, 1, this is equal to, okay, the power set of S. Okay, power set is going to show up a lot. Okay, let's go further with this. So, not only are we talking about functions, but there are special types of functions that we want to talk about. Okay, so the idea is as follows. Let's say you have a function from S to t. There's going to be 3 types of functions that go as follows. One of them is going to be called a one-to-one function. Okay, and sometimes it's called an injective function. Okay, and it goes as follows. It's again, the formal definition is given in the book, but it just says as follows. Given a guy over here, so this is in S, this is in T, this is a little t, there are no 2 guys here, S1, S2, that both go to the same place. Okay? In other words, there's no 2 things that go to one thing here. Okay? In class, I always say, here's the set of students, here's the set of chairs, okay? And when you sit down on a chair, you get a seat, you make a seat. Well, we don't allow 2 students to sit on the same chair, so that's that. Another way of saying it is, okay, that's it. There does not exist 2 things that go here. Okay. Let me just say it one more. There is at most 1 element in S that comes to an element in T. Okay, not 2, not 3, not 4. Okay. Another type of function is an onto function. It's also called surjective. Okay, surjective. Okay. And what that means is, here's S, here's T. It means for every guy here, there is some guy here that's on that hits it. That this element with this function f hits that t. Okay? So again, if this is the students and this is the chairs, then the function is onto or surjective if there's no empty chairs. Okay, if there's no empty chairs. Okay, then there's one more thing, okay, and the way to look at it is as follows. Here's you have all functions, okay, and some of them are 1-to-1, that's the way you write 1-to-1, okay, you could write it, and some of them are onto, that's this, okay, and if you're 1-to-1 and onto, then you're in here, okay, and that's called an isomorphism. Okay, a function is an isomorphism if both no 2 things go to one thing and everything here gets hit. Okay, let's just say it another way, a little bit more English. What 1-to-1 means is there's at most 1 element that hits every t. Okay, there's at most 1 element that hits every t. What onto means is there's at least 1 element that hits every t. Okay, great. So what an isomorphism is it's both at most 1 and at least 1, so there's exactly 1. So what an isomorphism is from S to T is, for every one guy here, there's exactly one guy here that hits it. And this guy can be exactly hit by this guy. And this guy is exactly hit by this guy, and there's no other one. So in some sense, it's a matching. Okay, it's a matching. So the number of my fingers on my left hand is the same as the number of fingers on my right hand, and I can match them like that. Okay, so that's what an isomorphism is all about. Okay, and we have a little notation that we're going to use for the rest of the class, and it says as follows: if you have S and T and there is an isomorphism, there exists an isomorphism, then we write it like this. Okay, it's like equal but with a little twiddle. The two sets are not the same. So for example, when would you have an isomorphism? If the number of students and the number of chairs are exactly the same. Okay, and so you have no two students sitting on one chair, and every single chair is occupied. So then you have an isomorphism, and when you come into class and you sit down in a chair, you are making this isomorphism, you're making this matching between student and chair. Okay, so these are the isos. We're going to spend a lot of time talking about isomorphisms in the rest of the class. Okay, we're going to talk about it even in 10 minutes. Okay, great. So these are special types of functions. Okay. There's another kind of operation on sets. Let's say I give you the set S and I give you a set T. Well, then we can look at the set of homomorphisms from S to T. Okay, so let me just say what that is. So we can look at, here's S, here's T. We can look at all possible functions from S to T. Okay, and it turns out that also, the set of functions, okay, well, the collection of functions also forms a set. So here's a set, and then you can have this other set, which is all functions that correspond, all functions from S to T, that's also a set. Okay, so that's an interesting thing. We also sometimes write this as follows. It's T to the power of S. Okay, you'll see why we do this in a second. Well, I'll tell you now why we do this in a second. Why we do this? Because you might ask yourself, how many elements are in this set? Okay, and the answer is as follows. So, how many functions are there from S to T? And the answer is, look how many elements there are in T. Look how many elements there are in S, and that's exponential like that. So let's just do an example. If there are 5 elements in T, and there are 3 elements in S, okay, so how many functions are there from the 3 element set to the 5 element set? And the answer is as follows. Well, for one of the elements, I have 5 choices here. For the second element, I have 5 choices here. For the third element, I have 5 choices here. And so I have 5 times 5 times 5 possible functions from this set to this set, okay? And we can write that as 5 to the third. So because we're dealing with exponentiation here, we might as well write it over here. So these are just 2 different ways of writing the same set. So this is the set of all functions from S to T. Let me show you where we've already seen this already. Let me show you where we have already seen this. Okay. Okay. So the set S with a star on top of it. Okay. What is this? This is the 1 element set. This is with an asterisk, let's say, okay? And this is the set S, and I want to know how many functions are there from here to here. Well, the answer is the number of S, the number of elements that there are in S. You're just choosing for each one of these, there's only 1, you're choosing an element here. Okay, so another way of saying this is that this set, the set of functions from here to there, is the same as the set S itself. Okay, you can figure out the elements of S by looking at functions from this 1 element set to that. Okay, now let's just write it another way, just so that we can see a million different ways of writing it. Okay, so this is a core idea, namely that you can determine a set by looking at functions. Okay, and they're isomorphic. They're the same thing. Okay, let's do another one. The power set of S. Okay, we said we can characterize the power. We can characterize a subset of S by looking at functions from S to the set 0, 1. Okay, so from S to the set 0, 1, we call that the characteristic functions. Okay, and again, you can write this again as hom the set 0, 1 to S. Okay, great. Now I'm just going to mention something. We're not going to go through all the details, but we're going to mention it. Hom, want to see how this hom function, this function sets, so this is an example of a function set. Okay, it's a set of functions. How it relates with the Cartesian product, which was the first operation we saw. So it goes as follows. S cross T, comma U. I want that a capital U. Okay. Is equal to, I'm not sure about the equal, but maybe it's isomorphic to, hom of S, oops, I'll do it like I do it in the book, T, comma, hom of S, comma U. Okay, so that's an important, that will be important chapter 5 and 6, but let's just say what it means. It says if you have a function f and it has two inputs, an element in S and an element in T, and it outputs an element in U, okay, well, that corresponds to another function, we'll call it f hat, which takes an input T, okay, so it picks one of these guys and says, okay, let's say I give you one of these guys. If I fix an element here, or if you want, you can say hardwire an element here, then what's left? Then this will correspond to this, so if there's another function from S to U. Okay, so okay, let's just go through that again. If you have a function that has two inputs and it has a third an output, okay, well, that's going to correspond to a function f hat, which takes t and hardwires the t, okay, and what you're left with is a function from S to U, and that's S to U. So here's two ways of describing the same type of function. This is sometimes in computer science it's called currying or things like that. We're just mentioning it now, but there's an example in the book, and you can see it very clearly. I just want to write this in another notation, in this other notation, because you can see it a little bit more clearly. What it says is U to the S cross T, that's this, is isomorphic to U to the S, that's this, S to the U, U to the S, that's this, to the T, okay? Now, these are three sets, but we've seen such notation when we're talking about numbers, okay? Exponentiation of numbers satisfies this requirement. So that takes care of that. Okay. Okay, great. So let's just back up and remember what we're doing. We're talking about sets. We're getting intuition about sets and about categories from sets and functions in between them. So we introduced sets. We talked about operations on sets. Then we introduced functions, and we talked about operations on the functions. Okay. In particular, the collection of all functions forms a set itself. So in some sense, this is another operation on sets. Given a set S, given a set T, you get another set, hom ST, which is a set of all functions from this to this. Great. Now, for the next few minutes, I want to talk about operations on functions. Okay, and we're going to have three operations on functions. The idea is as follows: given one function, given another function, how can you create a third function that is similar to it? Okay, so the first operation we're going to have is the simplest, namely composition of function. Okay, so let's see what that is. If you have a function S from S to T, F from S to T, and you have a function G from T to U, then we can compose this function, and we call it as follows: F compose G. Okay? Okay, I'm sorry, I said F compose G, but I wrote it backwards. Now this is going to be an issue, okay? In category theory we do this. Most category theorists do this, okay? Namely, we write functions somewhat, it might seemingly be backwards. We first do F, then we do G. We write this as G composed F. This little circle is the composition operation. Okay? And the idea is as follows: if you have a little guy here, S, then you go to a little guy there, T, and this little guy here, T, goes to this little guy here, U. So in particular, if you follow this around, S goes to little u. Well, that's what this function does. It takes little s to little u. So that's the composition. It takes this little guy and does what this guy and then this guy, which gives you exactly that. So that's what the composition of a function is. Okay, we have two rules. We're going to do some examples of compositions of functions in a second. I'm assuming you've seen it somewhat before, but we have two rules that are very important, and they're important every single time we see a category. We're going to see these two rules over and over. Okay, so let's say you have more than just three sets, but you have four sets. So you have S and T and U and V. Okay. Okay, and let's say you have a function here, F, and a function here, G, and a function here, H. Okay, let's see how we can compose these. Well, we can compose these and get F circle G. Again, I'm reading it backwards. Okay, or we can compose these two and get, okay, G circle H. Okay, now with this, I can do another composition. Watch this. I can do F, I can do this map followed by this map, and I get this map, which is F circle G, that's one map, circle H. Okay, and that's one map from S to V. And basically it works the same way. Take a little guy here, do what F tells it to do to that little guy, take that little guy, do it to here, do it to here. Okay? But I can also do it this way. Okay? And I get what? F circle G circle H. Okay. Now, it turns out that this function and this function are the same function. Okay? They do the exact same operation. Obviously, we're describing them in different ways. Okay? We're giving them different names. That's a different name than that. Look, the parentheses are messed up. The parentheses are different, but they are the same function. And let me just tell you what the function is. We can write this function, both of these is here as follows. There, take a little guy F, S, do F to it. Then do G to that, do G to the out. So S is the input, F of S is going to be the output. Do G of that, so you're now over here, and you're going to do the just G operation, okay? And then you're going to get an output for that. Do H of that. okay, and you're going to get an output over here. So both of these ways of describing the function is basically equal to this. Okay, and this rule is called associativity. Okay, and the idea is as follows. Composition of functions is associative. Okay, so you might remember this from elementary school. Addition is associative, subtraction is not associative. Okay, well, composition of morphisms is associative when we're talking about sets. Let me show you another idea. I'm sorry, another composition of operations. Okay, so you have f goes from s to t, okay, and then you have the following. Identity of s composed. So we said every single set has this funny function that does really nothing. It's just the input is the same as the output. Well, if you compose that with f, you're going to get, guess what? F. Okay. There's another function on t, and it goes as follows. ID of t. This is a function from t to t, and basically for input, any input t, it outputs the same exact input. Okay, and we have the following. F compose identity of t is equal to, let's just see what this is. Ready? If I first do f from s to t, and then I get an output of here, and then I do the identity on that, which means whatever the output is, the input is, whatever the input is, the output is. So I compose these, I get f like that. Okay, so these are like adding 0 to a number, doesn't change it. Okay, you're doing it on both sides. Or multiplying by 1, doesn't change it. So these are called, this is a unit law. Okay, I just would like to do this in terms of maps, and we do it as follows. I just want to show you these two equations in terms of maps. What it says is as follows. Start with s, do the identity of s on s. So this is that silly map that does really nothing. Okay, then do f on that to get to t. Well, what this says is, if you do the identity on s and then you do f, that's the same thing as just doing f. You don't change anything. That's the whole point of, so you take this input, you get back the same output, then you do f of it, you get back the same thing. Okay? But another way of doing this is, you can also, so here's f, you can also compose f with that silly function called the identity on t, okay, and guess what? I'm sorry, I should have written this as f composed identity on s, okay, and so this becomes f composed identity on t, so this is f, which is equal to identity on t composed s. Okay, so here's a nice little diagram that describes both this rule and this rule. This commutes, and this composed with that commutes with that. So just two rules about f. You can compose it with the identity before, you can compose it with the identity afterwards. Okay, great. Okay, this is called the unit rule or unit law, and the idea is as follows. Every single time we have a category, okay, we're going to always make sure that these two rules are satisfied. Okay, we're going to see this more next chapter, next video, but these two rules, associativity of composition, and that these identities act like zeros or ones, they act like nice units, that's what we use. Okay? Okay, so now some examples of composition. Okay, and there's some more in the book, but I just want to mention 2 or 3 here. Okay, I just want to mention 2 or 3. Okay, so one thing is evaluation. Okay, so given a function from s to t, sometimes you want to evaluate that function on one particular element. Okay, so there's one little s, member of S. Okay, and you want to say, hey, what's the value of this S when you do F? Okay, and the answer is you can look at that as composition of functions. And here's that same triangle we saw before, but now we have it like this. You have the star, okay, and you have the set S. Okay, I'm going to call this G. Okay, and then I'm going to have this function f from s to t. Okay, we have that function. Okay, and now what's this? What's this composition of this? So what this says is you pick out this one element and then tell me what the output of that one element is. So this is f compose G, and basically what f compose G does, it goes from star to t, and basically the star goes to, we evaluate f of s. Okay, so that's the evaluation of f at point s, and so we have that. Okay, so evaluation is an example of composition. Let me give you another one. Okay, and the idea is as follows. Again, you go of f goes from s to t. You have an inclusion function. A includes into s. Well, guess what? So the way to think of this is you have a function that on all of s gives you something in t. Well, you have a subset of that, a subset of s, and so I want to know what this function does on part of s. Okay, and you might think of this as follows. Here's your s, here's your t, here's f. Okay, now I have a subset of s called a, and I want to know not what the whole function is, but what the restriction function is. Okay, and we write the restriction function like this, with a long f restricted, with that long line. Okay, and we can again see this restriction function as a form of composition, and it goes as follows. You have A including I and C into S. You have S going to T. This is the function that you're dealing with, and then this map from A to T, this map from A to T is basically F restricted. Okay, so those are two examples of composition. Now I want to do something else. I want to show you that those three properties that we had about functions, namely, one-to-one, onto, and isomorphisms, injective, surjective. I'm sorry, I didn't tell you this, but another word for isomorphism is bijective. It is both this way and this way, so bijective. Okay, so we had those properties. I want to show you how you can describe those properties using composition of functions. Okay, so we had that before. So let's do it like this. F goes from S to T is one-to-one. So that's one-to-one, injective. If there exists a G from T to S. Now think of this as going the opposite way. So F goes from S to T, G goes from T to S, goes the opposite way, such that S, F, T goes to S, here's your G, and that's equal to the identity on S. Okay, so that's what it means to be one-to-one. Okay, if you want, you can think of this as follows. F is doing something, G is undoing it. Okay, and the idea is as follows. If you do something and then you undo it, if you get the identity, that means the function is one-to-one. Okay, let's talk about the idea of two things going to one. Look, if you have two things going to one, then there won't be a way of undoing it because you don't know which way to undo it. Should you, if you have two different things going to one, you don't know which way to do it. So that's why you need this. So we say as follows: it is one-to-one if there exists a unique way of undoing those things. Okay, so let's just think of it this way. You have S1 here and S2. If they both went to T, little t over here, then question, which, so S1 goes to T and S2 goes to T. Let's write it up. Okay, great. What should G take little t to? Should it take it to S1 or should it take it to S2? Should it undo what F's doing over here and here? And the answer is, there's no answer, okay? Because it won't work. So it will work when there are no two things going here, then you can undo what F did. That's exactly what this is all about. Again, in the book is a little bit more technical, and I go through exactly what I just said, but with symbols. Okay, great. Let me show you what onto means. Okay. F from S to T is onto. Okay. Again, if there exists a function from T to S, which can undo it. Okay. But here we have composition the other way around. T goes to S. This is G. F goes to T, and here we have the identity on T. Okay, let's see what this says. This says there's a function from S to T. S to T is onto means every single element here can be undone, which means that I can take. That means, well, let me just say it. What it means is that for every T, I can find some element S that lands on it. Okay, so let's do it like this. Here's your S, here's your T. What does it mean to be onto? It means for every T here, there's some guy here that goes to it. Okay, another way of saying that is, so this is F going this way. Another way of saying that is that there's a map from here to here, which picks out at least one guy that hits it. Okay, so that's this G. So this G says there is a map that takes T to this little S, and if I compose it, first I do G, take T, go back to the person, the element that's going to hit it, and actually hit it, I get the identity. I'm going to get back doing exactly the identity. Okay? Okay, so that's very nice. Let's talk about doing and undoing. If you can undo something and then do it, so that's the identity. Then you're going to get the original thing. Okay, so that's one-to-one, that's onto, and now we have the third property of functions, namely, isomorphism, or bijection, or bijective, okay? And we write this as follows. Well, what did we say? When is a function an isomorphism? Well, if it's both one-to-one and onto. Okay, so let's combine both of those diagrams and we get as follows. S goes from F to T. T, here's your G, goes to S. This is the identity on S. Okay, this is the identity on T, and here's your F again. Okay, and it says F from S to T is an isomorphism if there's some function here that undoes what S does, and also if you undo it and then it does this. So these are two what's going to be called commuting diagrams. We'll talk about that later, but basically it says as follows. If you go like this and like this, that's the same thing as doing the identity, and if you go like this and like this, that's the same thing as doing the identity. Okay, I'd like to show you this diagram slightly different. Okay, I'm sorry, not slightly different, but differently, But this second diagram is going to show up literally 5 more times, 10 more times in the book, or variations of it will show up 5 or 10 more times in the book. And the picture I want to do is similar to this. I might not have enough room, so I'm going to erase this because we're going to run out of room. Okay, and again, this is such an important diagram because we're going to see variations of it over and over and over. And it goes as follows: S to T. You have a function f. I want to describe what does it mean that these two are isomorphic, or f is an isomorphism. Well, what it means is that there's a function that undoes this. Okay, it's called an inverse. Okay, and it goes like this. Now, besides this, we have the identity on S. We can write that as follows: ID of S. Besides T, we have the identity on T. ID on T. Okay, that's great. So we have now 1, 2, 3, 4 maps. I'd like to draw 2 more maps. Consider this: start at S, do F, do the composition with G, and we started at S and we ended at S. So let's do that again: F to T, T to G to back to S. So here's another function from S to S. We're going to call this F compose G. Hold on, don't move. Okay, here's another map from T to T. You ready? G composed F, get another map like this. Okay, and so this is first do G and then F. Okay, great. Now, what isomorphism says, hold on, don't move. What isomorphism says, and this is extremely important, is that these compositions are equal. I'm sorry, these 2 maps are equal. The identity of S is equal to F composed G. The identity of T is equal to G composed F. Okay, they're actually equal. So these 2 maps are equal. Now again, we're going to see variations of this over and over and over throughout the textbook. But if we have to understand this first one, and then we'll understand all the rest of them too. So this is what it means for a map to be an isomorphism. F is an isomorphism if you have this. Okay, so this is, again, composition is very, very useful to see lots of properties. Okay. Another operation, so we have composition, but there's another operation that's also important, and it's called extension. Okay. The idea is we can extend a function from one set to the other set. Okay, so let me just give you an example first. Okay, so here's a function that every professor or every teacher does at the end of every semester. They take the set of students okay, and they assign A, B, C, D, E, no, not E. I don't know why not E. Okay, I guess E would stand for excellence. F, okay? This is what a professor does. This is what a teacher does. They assign a grade to every student. Okay, great. Okay, now let's say you have students and then you get more students. You get more students in your class. So you might write this as follows. You have, whoops, sorry. You have original students. Okay. And you include that into original students and new students. Okay, so you have the set of original students, and now you have an extended set, a larger set. Okay, and the idea is as follows. you have this function that gives a grade to every original students, but now you need a new function, and this new function, what it should do is not only give a grade to these original students, but also the new students also. So you might call this f, and we'll call it f hat, because it extends f. Okay, so this is another type of operation that you would have. This is an inclusion, okay, and it's not really an operation in the following sense. There's no exact way of doing it. How do you give the new students grades? But one thing you definitely want is that this should commute in the following sense, that if you look at the original students and you look at look at them from here, then this function should take the original students to the same grades that this function takes them to. Okay, so that's the sense of inclusion. Okay, I'd like to draw this another way. Again, the book has some more examples, but I'd like to draw this another way. So think of it as follows. Here you have the set S, and you include S into a set, here's the set S again, but into the larger set T, okay? And you have a function from S to U, okay, F, okay? And now what you want is a function from the larger set T into U, okay? But main point is it should extend this function. In other words, the values on these guys should be the same as the values on these guys. So f hat has to respect f in that sense. Okay, but here's the kicker. Here's the kicker. We're going to talk about, later on, we're going to talk about extensions, and even now in the book I do an example where this is not necessarily an inclusion. Let's say you just have a function from here to here, from S to T, don't want to think about that, and it's not an inclusion. It's just a function from here to here. So question, can we extend this function so that this still commutes? So that's called an extension. Okay, great. Okay, let's talk about the third operation. The third operation is called a lifting. A lifting, you're lifting something, and I'll show you what I mean by that. Okay, and it goes as follows. Let's say you have a function from S to T prime. Okay, and this is your function f, and you want to lift this function. Now let me explain to you what I mean by lifting. There's another set T, and there's a function from T to T prime. We're going to call that P, okay, like a projection. If you want, you can think of it as a projection, but the way to think of this is a large set, and this is somewhat of a smaller set, and you're giving values here. Question, can you lift this function from this small set to this larger set? Okay, we call that a lifting. Okay, okay. So we need, we'll do two simple examples of this. Okay, one simple example is as follows. This is a really simple example. Okay. Okay, you have a function from here to here. Okay, but this is a one-element set. So the one-element set is basically going to pick out an element here. Okay, but now what we want is a lifting of this function to here. So here's the point. Question, can you, or what would a lifting be? Well, a lifting would also be from a one-element set to T, but we want this to commute. So what that means is there's T to T prime, okay? I have a function that maps onto, that maps into this T prime, okay? So there might be a few different T's that map into this thing. So let's call this little t0. This is going to map to little t0. So let's do it like that. We have that. Little t star is going to go to t0. Now there might be a few different objects here, T1, T2, T3, and they all map into T0. Don't forget your tails on your map, okay? They all map into T0. What this function requests, the lifting of such a function, chooses one of these three guys who goes there. Which one does it choose? Doesn't matter, okay? We'll see different requirements in a second, later on. Okay, let's do another little slightly political example. Okay, so let's assume like this. This is just you have U.S. citizens. You have U.S. citizens. You have U.S. states. Okay, so there's 330 million here. There's 50 states, okay? And now you have a function P, which takes every citizen to the state that they live in, to the main state that they live in. Okay, constantly looking for new markers. Okay, so I have 330 million people living in 50 states. Okay, and now you have a set A, B, C. Okay, and you have a function. And basically, this function chooses three states. Question, or a lifting, what would a lifting do? It would choose three citizens who live in those three states. So that's what a lifting is. That's an example of what a lifting is. Okay, I take this example and in the book, I take this example and I go further with it, and it's a little bit more interesting. Okay, so these three operations. Now let's just summarize our three operations. Okay, so you can summarize them like this. It's a nice triangle. And you have composition. Okay, let's just remember what composition is. If I give you a map like this and I give you a map like this, then you can compose it like this. Okay, there's also the extension, and what's that about? If I give you a map like this and I have an inclusion over here, then the extension extends this map from the smaller set to the larger set, so that's this. So again, erase this for a second. An extension takes a map like this and a map like this and gives you a map like that, okay? And finally, a lifting says what? Given a map like this and a map like this, a lifting is a map across like that takes it. So these three things are intimately connected. Okay, these three operations on functions are intimately connected. Okay, great. Okay, good. Now, I want to finish off this class talking about three different structures that are based on sets that will show up over and over and over again. Okay, so we've become experts on sets. We have all these operations. We have operations on the sets. We have operations on the functions. Okay, and so I want to talk about three different structures that show up they're based on sets. They talk about sets, and they're going to show up the rest of the class. Okay, I'm going to go a little bit quickly through them, simply because this has been a long class, but also because you're going to have to get the details in the book. You're going to have to see a lot of them. Okay, so first, so let me tell you what the three structures are. We're going to talk about equivalence relations. We're going to talk about graphs and graph homomorphisms, and we're going to talk about groups and things called group homomorphisms. Okay, so let me tell you what an equivalence relation is. Okay, I'm getting frustrated with the damn. We got a good one. Nope, no good one. Hold on. Okay, So let's talk about what an equivalence relation is. Okay, so first, before we talk about an equivalence relation, we have to talk about something else called just a relation. Okay, and so what's a relation? So here's a set S, and this is ordered pairs of elements of S. Okay, so take any non-empty set S, and well, it can even be empty, but the ordered pairs of these elements. Okay, a relation is a subset of that. Okay, and what it is a way of describing how elements of a set are related to each other. So you might have S1 and S2, and you want to ask yourself, are they related to each other? Okay? And again, there's a lot of different sets and there's a lot of different relations in between them, and it depends on which ones you're dealing with. Let me give you two examples. You have S is the set of all people in the world, so S cross S is like that. This is pairs of all people, and you want R, I'll call this RSIB, okay? And these are siblings. Question, are these two people, are they siblings to each other? Okay, is one a brother or a sister to the other? Okay, okay, and so you have X comma Y is a member of R if they are siblings, and you have X comma Y is a member of R, is not a member of R if they're not siblings. Okay, so most people on the planet Earth are not siblings to each other. Okay, so that's one example. Let me give you another example. Okay, you have S, the citizens, U.S. citizens, and you have another S, okay, and you have R, I'm going to write ST for state, that's a subset, okay, and X comma Y, two citizens, are a member of RST if and only if, okay, so here's a definition of what the relation is. X and Y live in the same state. Okay, so again, there are 50 states in the United States, okay, and if they live in the same states, then they're related to each other. Okay, so this is a typical example. Okay, great. So there is a lot of different relations, and I give a lot of different examples in the book, but what I want to do now is, just like I talked about functions, and I said, okay, let's talk about special types of functions, so too, there's relations, and I want to talk about special types of relations. Okay, and we're going to have three different properties. Okay, I'm going to say a relation is reflexive. Okay, what does it mean to be reflexive? It means X is, it means for every element X in S, we have X comma X is a member of R. In other words, everything is related to itself. Okay, so let's talk about that in the two examples I gave. Siblings, you are not a sibling to yourself. Nobody's a sibling to themselves. Okay, so that doesn't make sense. So it's that relation of being siblings is not reflexive. Okay, what about living in the same state? Do you live in the same state as yourself? Answer, yes, you do. So it is that relation is reflexive. Let's do another one, symmetric. Okay, and what that says is for any X comma Y member of S, okay, X comma Y is a member of R. If X is related to Y, that implies that Y comma X is a member of R. Okay, so if X is related to Y, then Y is related to X. Okay, so that's called a symmetric relation. If that's satisfied, it's called a symmetric relation. Let's go through our two examples. If X is a sibling of Y, then Y is a sibling of X. Yes, it is. If X lives in the same state as Y, then Y lives in the same state as X. Yes, it is. Okay. Okay. Another property, and we're going to see later on in chapter 2, we're going to see even more properties of these things. But now we're just going to deal with these three properties. Another property is called transitive. Okay. Transitive, and that's as follows. That has to do with three things, X, Y, and Z. member of S, and we have the following. If X comma Y is a member of R, and Y comma Z is a member of R, this implies that X comma Z is a member of R. Okay, so basically what this says is if X is related to Y and Y is related to Z, then X is related to Z. Okay, let's go through our two examples. Siblings, okay. The siblings is a little bit more complicated. It depends what your definition of a sibling is. Is a sibling a full, shares both a father and a mother? Then yes, this is transitive. But what happens if it just shares one parent? So we're going to call a half sibling to be a sibling. Or let's talk about the other relation. Let's talk about a half sibling, or half sibling and a whole sibling. Okay, and the point is as follows. That might not be transitive. Let's go through it. If X is related to Y because they share a mother, and Y is related to Z because they share a father, then X has absolutely nothing to do with Z. They don't share anything. So half siblings would not be transitive. Okay, great. Let's talk about U.S. citizens. Okay, if X lives in the same state as Y, and Y lives in the same state as Z, then X lives in the same state as Z. So it is. Okay, great. Okay, now these are special types of relations. Now I want to talk about what an equivalence relation is. An equivalence relation is a relation that satisfies all three of these properties. Okay, and so the way to think of this is in Venn diagrams. If you look in the book, you'll see I love Venn diagrams. So we have relations, and some of them are reflexive, and some of them are symmetric, and some of them are transitive. Okay, and if they're all three, they are called an equivalence relation. Okay, now why should we care about these? Okay, equivalence relations is a fancy way of saying things are kind of the same. Okay, a relation that turns out to be an equivalence relation means you're measuring something which is kind of the same. Okay, so we take that. Okay, so if you have a relation R and it satisfies these properties, then the thing you're talking about, what are they relating, means they're kind of the same. Okay, everything is kind of the same to itself. If X is kind of the same to Y, then Y is kind of the same to X, and transitive also. Okay, great. Now, the main thing about equivalence relations is that given a set and an equivalence relation, we write that like that, okay? And what that is again, it's a subset of S cross S. It shows which elements are related to it. We write that sometimes like little s1, that's an element there, comma, little s2, that's a pair, is a member of twiddle. And again, the way to think of this is kind of equal, okay? Oh, another way of writing this is S1 twiddle S2, okay? They're related. They're very related. So given a set and a relation on the set that happens to be an equivalence relation, we can do that. We can form the following set. This is S slash twiddle, okay? Okay, and what this is set of equivalence classes. Okay, in other words, take a typical element of the set S, okay, and now we're going to look at equivalence classes of S. This is the set of all S prime such that S prime is related to S. Okay, so take those things that are related to it. So let's do our example with the siblings, okay? Then any person his equivalence class of that person is a set of all of his siblings. So that's very nice. Let's talk about two people living, this is a set of US citizens, and talk about two citizens living in the same state. So if Jack is one of those citizens, then the equivalence class, and let's say he lives in Wyoming, then this is the set of all people in Wyoming. Okay, so the way to think of an equivalence class is it's a subset of all the elements that are related to it. Okay, using this equivalence class, using this equivalence relation. Okay, great. So here's the main point. Good Lord. Here's the main point. Given, we shouldn't use this. Okay, given a set and an equivalence relation, you can form another thing called the quotient set. So this is the quotient set. Okay, and that's all the equivalence classes. Okay, so for example, I don't know, if you look at all people, you look at siblings, well, there's a hell of a lot of equivalence classes because every family is going to have, you know, just a set of things. If you look at the 320 million people in the United States and you look at who's living in the same state, so the equivalence classes are going to have 50 elements. I'm sorry, the quotient set is going to have 50 elements, okay? There's going to be a set, an equivalence class for New York. There's going to be an equivalence class for California. There's going to be an equivalence class for Wyoming, et cetera, et cetera. Okay, so for every set and for every equivalence relation, there is a quotient set like this. Moreover, there's a nice function like this. Okay, and what that does is it takes every element to its equivalence class. So if Jack lives in Wyoming, it's going to take him to the Wyoming thing. Okay, another example, if you're talking about siblings, so if you're going to talk about Jack, okay, so he's going to go into the set of all equivalents, he's going to go to his set of siblings. Okay, so that takes care of that. So that's all about equivalence relations. There's more examples in the book, and it's a rich field which we will cover later. Okay, great. So I told you that at the end of this section, we deal with 3 different topics that are based on sets, and so I want to go on to the next topic, and the next topic is called directed graphs. And I'm sure you all know what a directed graph is because I teach it in elementary school, but what I'd like to do is I'd like to show you the definition, because the definition is going to be very reminiscent of the definition of categories. So it's going to be like that. Okay, so what's a directed graph? Well, it's got vertices, okay, and it's got arrows between the vertices, okay, and it could have something like that. Okay, so that's a directed graph, but I want to be more exact again, and the book has a million examples of directed graphs, and that's fine, but I want to be a little bit more exact with the definition, again, because we're going to see it something similar when we get to categories. Okay, so G is a directed graph. It consists of 2 sets, V of G, vertices of G's, dots of G, okay, and A of G. Sometimes you'll see E of G because they're talking about edges, but here we're talking about directed graphs. We want direction. So if there's a map from here to here, there's no map from here to here, okay? There's a map, you can make a map from here to there, that's fine. But we're talking about arrows, so we're talking about directed graphs, okay? So you have the set of vertices of G, you have the set of arrows of G, okay, and then you have 2 functions. One function is called SRC of G, and it goes from arrows of G to vertices of G. Okay, and I'll show you what it is in a second. And then there's another one called T, no, let me do it the way I have it, TRG of G, and it also goes from arrows of G to vertices of G, okay? And the way to think of this is the source of an arrow, and this is the target. So for example, if you have This is a directed graph, and this is element P, and this is element, this dot is element Q, okay? Then, and this arrow is, let's say, little f, then SRC of little f, okay? The source of this, where is it coming from, is P, okay? P, which is a vertex. The target of G of little f is Q. Okay, so it comes, here's the main point. Every arrow has a starting point and an ending point. And these functions tell you what it is. Okay, so if we're talking about H here, and this is the letter K, and this is the letter T, then H starts at T, the source of H is T, the target of H is K. Okay? Okay, and that's it. That is the definition of a graph. Okay, so let's go through it again. The definition of a graph is two sets, 1, 2, and two functions like this. Okay, and that's it. You can describe any graph like that. Okay, now what we're going to find is we're going to want something which you might not have seen. Okay, and that's called a graph homomorphism. Homomorphism. And this is a map between two graphs. So if you have one graph here and you have another graph here, you can have a map between them. So this is very similar to having, you have a set here, you have a set here, you have a function between them. Okay? So let's just do another type of graph here. So we'll do something simple like this. Okay, and there's lots of this. So here's another graph. So here's one graph, here's another graph. And now a graph homomorphism is a map from one graph to the other graph. Okay, now how does it work? Well, there's lots of graph homomorphisms from here to here, but we're going to have some requirements. So let me tell you what a graph homomorphism is. Let's say this is graph G, and this is graph G prime. So a graph homomorphism is a function. Well, it's a pair, it's a pair of function. But we write it as follows. H goes from G to G prime, okay? And there's two parts of this function, okay? In other words, we write it like this, but really it's two functions, and it goes as follows. There's the vertex part of it, and it goes from vertices of G to vertices of G prime, and also H of A, and this goes from arrows of G to arrows of G prime. Okay, and again, the reason why I'm going through this is because there'll be similar definitions between, so let me just foreshadow a little. Okay, you ready? Categories are souped up. They're graphs on steroids. Okay, so I want to know the definition of graph, a formal definition of graph, so I can know the formal definition, so I can get to the formal definition of categories. Okay, but another thing also is between two graphs, there's going to be the notion of a homomorphism, a morphism between two graphs, and guess what? Between two categories, there's also going to be a notion. Okay, so again, thinking of categories as souped up graphs, so there's going to be a concept of a souped up morphism, graph homomorphism. Okay, and by the way, that's going to be called a functor. We'll see that in chapter 4. Okay, now these two things, so you might say this T goes here, and this P goes here, and this dot goes here. That's moving the graphs. But also, what do we want? We want the arrows. This arrow might go here, and this arrow might go here, and this arrow might go here, etc., etc. So we have a morphisms. We have a graph homomorphism is a way that maps vertices in here to vertices in here, arrows in here to arrows in here. But we have two requirements, and the requirements are, I'll show you the requirements in a second. Okay, I'm going to write them and then I want to draw them. So it goes as follows. HV of SRC, okay, of G of F is equal to SRC of G prime of HV, damn. Okay, it's equal to SRC of G prime of HV of F. Okay. That's one of it. I'm sorry. HA of F. Sorry. I'll explain it to you in a second. I promise you'll understand it. Okay? So we're going to write it like that. And the other one we're going to write is HV of target, TRG, of G of F is equal to TRG of G prime of HA of F. Okay, that looks strange and that looks weird, but we're gonna write it in two other ways and you're gonna understand it, I promise you. Okay, but we have to see it the way it is. Okay. Okay, great. So we don't have a lot of room here. Let's do it. These two equations correspond to two squares. And the two squares go as follows. You have arrows of G. You have arrows of G prime. You have H of A. Okay, now for every arrow, you have a source of G, and this goes to vertices of G. And this goes to vertices of G prime. And you have another morphism here, which is H of V. Okay, again, and this is source of G prime. Okay, so this is an equation which says exactly this. This is about sources. Okay, and what it says is that the homomorphisms respect the sources. And I'll explain to you, I'll show you a picture of that in a second. Okay, there's another requirement. In fact, I can do it very, very quickly. And it's right over there. Okay, so write this down and then write this down. Okay, and what this says is, you ready? That the homomorphisms respects the target also. Okay, so this is just two ways of writing the same thing. Let's just show it. If you do H of A and then target, H of A and then target of G prime, that's the same thing as doing target and then H of V. That's that. Okay, so these two squares commute. These two squares commute. These two equations are equal. But let me show you another way to think about it. Okay, and this is the right way of thinking about it. It's done in the book, but let's do it. Okay, and the idea is as follows. You have a map over here, F. This is a map in G. Okay, and so you might say that this is source of F in G, and you might say this is target of G of F. So this is where F comes from, this is where F goes to. Okay, great. Now, what H is going to do is, it's going to take F to some map in G prime. Okay, so it's going to take H of A of F. Okay, so this part of the diagram is in G, this part of the diagram is in G prime. Okay, great. And we want, now, what should we call this dot? And what should we call this dot? So here's one way of talking about this dot. We can say this dot is as follows. H A of F, okay, and it's the source of that. Okay, so look at this. It's the source of that. Okay, let's do this one. This is TRG, target of G prime. This is a G prime of H A of F. Okay, so that's one way of looking at it. But there's another way of looking at it also. Namely, not only does this go to this, but it matches up with its source also. So another way of saying this is H of the vertices of SRC of G of F. Okay, what the requirement is that these two ways of talking about this dot is the same. In other words, if you move this point to here, what it's saying very simply is, okay, if you have this arrow in one graph and it moves to this arrow in the other graph, then you better make sure that this source goes to this target goes to this, and then the arrow moves over. Okay, so what we're saying is the arrows move, but with the source and target connected to it. Let's just finish this. This is H of V of TRG sub G of F. So look at that, apply H of V. And what we're saying is that these two descriptions of this dot must be equal. Okay? Another way of saying that is that the graph homomorphisms match, they keep sources and targets for where they're going to. Okay? They respect sources and targets. That's exactly the way to say it. Okay, so that's a graph homomorphism. And lots of examples of graph homomorphism. Basically, what's a graph homomorphism? It's a map from a graph to another graph, such that every vertex here gets mapped to a vertex here, and every edge gets mapped correctly with it, with its source and target mapped nicely. Okay? Okay, great. Okay, let's just look at some properties of graph homomorphisms and see if we can work with some of them. Okay, some are very simple and some are very similar to what we saw in set. Namely, how about this? That looks like an asterisk, but and there's another way of thinking of that. That's the one object graph. Okay, and then we have G, any graph, and guess what? What's a graph homomorphism from here to here? Well, it's something that picks out a vertex, because there are no edges in this graph. There's just vertices. So any map from here to here just picks out a vertex, and that's pretty simple. We saw that's very similar to what we saw about sets. Okay, great. How about this? Here's a graph. It's got two vertices and a line in between them. Okay, what is a map from there to there? Well, what it does is it picks out an arrow in here. So this picks out vertices in here. This is a graph. It's a stupid graph, but it's a graph, and it picks out edges in here. Guess what? We can do this. Okay. That's a triangle graph. That's a simple triangle graph. And a map from here will pick out some triangle in the graph. And by the way, the graph might not have a triangle, and then there won't be any morphism like that. This graph might not have any edges, and there won't be any morphism in here. This graph might not have even vertices. Okay? There's another graph, I think in the book I call it a snake graph. Okay. And a map from there to G is a sequence of maps like that. Okay, so one of the things we said in the beginning of this class is that, and in the last thing, maybe I said it, is that you can learn information about an object by looking at maps going into it. Guess what? You can also learn information about a map by looking at maps going out of it. I'm sorry, let me just make sure I said that right. You can learn information about an object in a category or a set by looking at different maps going into it. You can also learn information about an object in a category or set or a graph by looking at maps going out of it. So let's look at that. Okay, let's consider the following stupid graph. It has a map like this and a map like this. We'll call this A if you want, we'll call this B. It's a simple map, 2 objects, 2 maps, nothing to it. Okay, and I want to know, is there a map from here to here that's surjective on objects? What do I mean surjective on objects? It hits this object, there's something in here that hits this object, and there's something in here that hits this object. Now, I just want to say, if it's not surjective on objects, then there's one morphism, there's actually 2 uninteresting morphisms. Take every single thing, every single vertex here, and map it to that point. Take every single arrow here and map it to that arrow. That's a graph homomorphism. Okay, everything is satisfied. Here's another one. Close this off. Take every single vertex here and map it to there. Take every single arrow and map it to there. Damn. Okay, take every single arrow and map it to there. Okay, great. That's another graph homomorphism. Question: is there a graph homomorphism from here to here that lands on both arrows? And the answer is, if there is no surjective, that means onto, graph homomorphism like that, then G is, let me just state it correctly. Okay. G is weakly connected. Okay, what do I mean by weakly connected? That means for every vertex in here and every other vertex in here, there's an arrow from there to there. Okay, so again, if there's no surjective graph homomorphism, then like this, then it's weakly connected. The way to think of this is as follows. If you can partition G into 2 parts, okay, lots of arrows in here, arrows, vertices all over, and you can partition them into 2 parts, then you know what? You can send one part to here and one part to here, and then you'd be finished. But what that would mean is that this is not weakly connected because there's no way to get from any vertex in here to any vertex in here. Okay, let's do the opposite of that, contrapositive. If G is weakly connected, then you can't partition it like this, and so it's all one big happy graph, and therefore you're not going to get a surjective map. They'll either all go here or they'll all go there. Again, what we're doing here is we're looking at functions from here to here, and we're determining properties of that graph. And this is a central idea in all of category theory. Okay, looking at maps to determine properties of objects. Okay, great. Okay, just one more thing about graphs and then we move on to something else. Namely, not only can you have a graph homomorphism, but you can have 2 graph homomorphisms. And guess what? They can be composed. Okay, so if this is F and this is G, this becomes F composed G. Okay, and if you had 1, 2, 3, 4, you would have graph homomorphisms, homomorphism composition is associative. Okay, and we know what that means. That means if you have 3 of them, F composed G composed H, F composed G composed H, and it doesn't matter how you put the parentheses because they're equal. One more idea. For every single graph, there's a stupid graph homomorphism called identity of G. Okay, and basically what does it do? It takes every vertex, goes to the exact same vertex, takes every arrow, goes to exact same arrow, and that satisfies those 2 requirements that we have. So there's definitely one. There's definitely such a graph homomorphism. Okay, it's called the identity graph homomorphism. And if you have F composed identity of G is equal to F, okay, which is equal to F composed identity of G prime. So if you have a map like that and you compose it with the identity maps, it does nothing to it. It doesn't change. And these 2 requirements, I told you they would show up, and they're going to show up again and again and again and again, especially in the next video. Okay? So graph homomorphisms compose correctly, well. That's very nice. Next. Okay? Next thing is about groups. Okay, you might have heard of the word groups. You might not have heard of the word groups. It doesn't matter. It's a fundamental notion in all of physics and in all of mathematics. And we're going to show, basically, it's a set with a certain operation, with certain operations, and they satisfy certain things, and they show up all over when talking about the notion of symmetry, and they're going to show up all over in the book. Okay, so let's talk about it. First, we have to talk a little bit about operations. So if you have a set M, and you have another, and you do something like this, this is called a binary operation. Let's just see what it is. Okay, you can write it like this, A times B. You have an element A in here, you have an element B in there, then you can, this is pairs of the elements, and they go like that. So another way of writing this is, you have an element here, you have an element here, they go to an element A times B. This is a binary operation. There could be many different binary operations. We can call it F, we can call it G, we can call it times, we can call it minus, we can call it division. There's lots of different notations that you can use, but the main point I want to bring out is a binary operation on sets takes pairs of things and brings out one of them. Okay? There's also something called a trinary operation. What does it do? Well, it takes triples of things and gives out an element. Okay? So what happened here is this would be A and B and C. This is an ordered pair, and they would go to, I don't know, F of A, comma B, comma C. Depends how you write this operation. So this is a trinary operation. Guess what? You can have an n-ary operation. That takes n elements, okay, and puts out one of them. So we have a binary operation, a trinary operation, dot, 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 an n-ary operation. We also have a unary operation, okay? So what does that do? Take a number, take an element, and it does something with just one of them. Let me give you an example of a unary operation. Take any whole number, put a minus in front of it, then you get the negation of that whole number. That's an example of a unary operation. Okay, so notice 1m, 2m, 3m, nm. Okay, but there's something else. Okay, and that's called, hold on, what do I want to call it? I think a constant operation? No, I want to, so this is a unary operation. Okay, I want to call it a zero-ary operation. Okay, and basically that takes 0 copies of this M, and for reasons that will become apparent later, that turns out to be a 1-element set, and M. Now, we've seen this before. We spent the whole class talking, from the beginning of the class we've been talking about this. What is this? This picks out an element of M. Okay, but another way to think of it is it's a zero-ary operation. It's an operation that just picks out an element. Okay, so it's very interesting. Combining elements with different operations is one thing, but another thing is picking out an element is also. So all these are about operations. Now let me tell you what a group is. And again, the formal definition is in the book, but I can say what it is. Okay, a group is G. Don't get confused with G is a graph, G is a group. Now we're talking about groups. G is a set. Okay, it has a binary operation. This is the main part of it. Operation. Okay, we write it as star. Star is an overused object here, but it's a binary operation. In other words, it takes 2 of them and it puts them together as 1. Okay, and then 2 more things. One is a unary operation. Okay, U. I'm sorry, I don't want to call it U. I want to call it, and it goes from G, and it outputs another element of G. So this takes, you plug the number in here, you get another number that's in there. You plug the element here, and you get another element in there. Okay, it also has a zero-ary operation. A zero-ary operation, okay? And so what's a zero-ary operation? Well, I'm going to write this as V, okay? It's a star to G. It picks out 1 element of G. The 1 element we're going to call is E, and it's going to be called the identity element. Okay, now, these 3 operations, 1, 2, 3, these 3 operations have to satisfy something. Okay, they have to satisfy 3 rules. Well, 3 rules, but let me just, I'm going to write the rules, and then I'm going to draw a picture of the rules. And this is a fundamental notion. Okay, we're always going to be drawing pictures, which is commutative diagrams about rules. Okay, so let's do it. So the 3 rules are very simple. For all, you don't like that symbol? Okay. So let me just say it. For all x, y, z in G, we have the following. X times y times G, z, okay, equals x times y times z. It's associative. We saw associative a lot today. Okay, it's associative. In other words, this binary operation is associative. That's one rule. Okay, and the next rule is that this unary operation undoes the classical thing. So let me just say what that means. Okay, again, I'm going to write it here, but we're going to erase this all. We're going to make nice pictures of this. X times x times x minus 1 of it. Okay, so that's times. So we're going to multiply. Okay, the way to think of this is take the number 3, multiply it by 1 over 3, and you get the number 1, which is the identity. Okay, so that's equal to E. That's the identity element. Okay, another way of saying this is x minus 1, it could be, the multiplication could be the other way, okay, times x, and you get the identity. Okay, so that's the second thing. Okay, and the third axiom is as follows: x times e equals x. So if you want to think of e as 1, take a number times 1, it's equal to the number. And you have to do it on the other side too. E times x is also. So these three operations, namely, they all contain this main operation, the binary operation, but what this says is the main binary operation is associative. It has an inverse, okay, and the identity, or the unit, acts well with respect to it. In other words, they act somewhat like numbers. Okay, that's the definition of a group, but I'd like to, since one of the things we stress in category theory is that it's not elements that are important, it's maps that are important. Functions are important. So what I'd like to do is I'd like to restate these three things in terms of maps. Okay, and it's done on page 31 of the book, but I'm gonna do it here and work it out with you because it's so fundamental. And let me explain to you why it's fundamental. And this is something we do all the time. We understand something in terms of sets and maps between sets, and then we try to do it in other contexts. We do it in other categories. So once we have an idea that we understand, we can try to do that same idea, but not with sets, which are obvious. We can do them with other things also, and we have to keep track of it. Okay? So this is something we're going to be doing over and over and over. We're going to see something in terms of sets, then we're going to abstract out of it and just get pictures of it, diagrams of it, and then we're going to do those diagrams in other categories, and we're going to get interesting phenomenon in other categories. So I said groups are very important for symmetry. We're going to find symmetries all over the place because of this. Okay, so let's talk about that associativity axiom. So we have as follows: M cross, what does it say? Why did I say M? Let's do G. Okay, let's do G. We have G cross G cross G. What does it say? It says if you have three different G's, three different elements of G, okay, you can multiply them in two different ways. Let me first write it and then do it. So you have, let's do this. This is star cross identity on G. I'll explain what that is in a second. And this is identity on G cross star. Okay. Let me show you what this says. We insist that this diagram commutes. That means start off with any triple here. If you went this way and then you went this way, that's the same thing as starting off the same triple here, going here, and then going there. Let's just see what happens. X, comma, Y, comma, Z. Okay. Now, this map is a funny map. What it does is it multiplies the first two and leaves the identity on G. It leaves this one alone. So this is going to take to X times Y, comma, leave Z alone. We're going to leave that alone. Okay, great. Now, this has two elements of G, X times Y and Z, and we're going to bring them together. And we might write that as, we should write that as X times Y, whoops, bring it together with this multiplication, Z. Okay, so that's one part of the diagram. But you know what? There's another way of looking at this. Look at this. X comma Y comma Z. Leave the identity on G over here and multiply these two. So this is going to give you X comma, leave the X alone, Y times Z. Okay. Okay. And now we're going to bring this to here by multiplying here. This is two elements of G. We're going to multiply them. So you have X comma Y times Z. So this is going to be X times Y times Z. Okay. The two different ways of associating things, and we insist that they are equal. Okay, so just saying this inner square means, just saying that this commutes means that this axiom is satisfied for all x, y, and z. Okay, and that's a nice thing to say. Okay, hold on. Okay. Again, these are on page 31. Well, let's do it again. So how about this? G delta G cross G Okay, this is part of another axiom. Let's see if we can make sense of this. Okay, there's a few things that we need to see. This is called delta. This is called the diagonal function. And what it does is it takes a typical element x and it takes it to pairs of x. So x comma x. What is G cross G? It's a set of ordered pairs of it. So this takes this to this. That's no problem. Okay. Let's do this. I'm sorry, this is V. Let's do this. Now, what does it say? We have to, which map should we do from G cross G to G? Well, the first map says leave X alone. Just leave the identity on this one. The second one says do the inverse on this. So this, the pair is going to go to this, X comma X minus 1. Okay, now this map is very simple, just multiply it. So this is going to be x times x minus 1. Okay, now this is a little bit more stranger. Let's do this. There's only one map from G is a set, to the one object set. There's only one map like that, and that just takes everything there. Okay, and this is that map that picks out the identity. So take x, it's going to go to star. Look at that, I have two different stars here. In the book I don't mess it up because I have more, I can type better than I can write. So x goes to that one element set and this goes to E. And now insisting that this commutes means this is equal to this. That means x times x minus 1 is equal to the identity. Okay, there's another, this is where you're multiplying the inverse on the right hand side. There's another diagram where you're multiplying it on the left hand side, and you can see that also. And the other requirement, namely that x times E is equal to x, okay, that can also be done with a commutative diagram. And so we like those commutative diagrams. Okay, great. Don't want to belabor the point. Okay, I'm sorry. In the book I go through lots of examples of groups, and I promise you we'll see lots of examples of groups and lots of examples of other mathematical structures also. But what are we interested in? We're not interested in groups. What are we really interested in? We're interested in morphisms between groups. Okay? Okay, so let's see what that would be. So let's say you have a group, okay, and it has a multiplication operation, and it has an identity, and it has an inverse, and it has identity. So this is one group. And then we have another group, we'll call it G prime. It has another operation, prime. It has another inverse, which goes from G prime to G prime, so we'll call it G prime inverse, and it has another E. Okay, well, E prime. Okay, what's a group homomorphisms? That's something like that. It's a function like that. Okay, we'll call it F, and it has to satisfy certain requirements. So let me just explain to you what it is. F is a function from G to G prime. This is a set, this is a set. But what we want is something new. We want it to preserve the operations. And I have to explain to you what I mean by preserving the operations. So it means as follows. F, and again, we're going to write this with elements, then we're going to draw pictures of it. It's going to say f of x comma y, whoops, times y is equal to f of x times f of y. Okay, so that means it's preserving operations. Let's just, whoops. This, x is an element of G, y is an element of G, x times y is an element of G. F of that is an element in here. Okay, now f of x is an element in G, f of x is an element of G prime. Y is an element of G, f of y is an element of G prime. Okay, now we could take this element in G prime, we could take this element in G prime, we can multiply them in G prime, and we get that. But what this is saying is we want f to preserve the operation. Respect the fact that there's an operation here. Okay, this is very, very similar to what we saw about graph homomorphisms. Okay, another operation. We want f of x inverse to equal f of x inverse prime. Let's go through this. X is an element of G. X minus 1 is an element of G. F of x minus 1 is an element of G prime. Okay, good. X is an element of G. F of x is an element of G prime. Take the inverse of that. What we're saying here is that we wanted to preserve the unary operation. Last one. F of E is equal to E prime. Okay, so basically we're going to have G over here, G prime over here. F is a function from here to here, but you can take two elements here and you can multiply them. Well, so too you can take the image of those two elements and you can multiply them. We want them to preserve. That's very nice. It's very helpful, but I want to look at it from the point of view of graph homomorphisms, and we're going to do this next video also for something called monoid homomorphisms. We're going to do this over and over, and the idea is as follows. What's a graph homomorphism? Well, a group homomorphism. It's a map from the group to the group, but there's a multiplication here, and there's a multiplication here. And here, this map takes f, from this f takes G to G prime. This f takes G to G prime, okay? And this is that. Okay, now saying that this commutes is exactly saying that this always happens. But here's a pretty picture of it, and again, we can take this pretty picture and we can put it in other categories, and so we like that. Let's do the same for here, although for reasons that are not important, this is not an important thing, but let's just do it anyways. Okay, you have G, G prime, you have F, okay, you have G prime, you have F, now you have a an inverse operation here, so this is minus 1, okay, and you have a minus 1 prime. Okay, saying that this commutes means this is true. Okay, so this picture corresponds to this. Okay, very nice. Let's do this. This is simpler as can be. This is as simple as can be. So let's do it again. You have G, G prime. This is your F. Okay, and this, I'm going to draw it a little bit different. Okay, here's your one element set, not your multiplication. Okay, and this picks out, I think we call it V, this picks out that one element set. this picks out the identity, which we call E. Here's V prime. This picks out an identity in G prime. And what do we want? We want, if you pick out the identity here, and then you do F of it, that's the identity here. So F of E is equal to E prime. Very nice. So this is a formal definition of what a group homomorphism is. It's very nice. Guess what we're going to talk about now? We're going to say that group homomorphisms compose. So let's do that. If you have a group, and you have another group, and you have another group, okay, and you can call this F, and you can call this G, then guess what? There's a group homomorphism, F compose G. You should be bored by this already. You've seen this before. Guess what I want to require of these group homomorphisms? Guess what's in fact true? The answer is H composed G composed F is equal to H composed G composed F. Boom, boom. It's associative. Okay, next idea. For every group, there's a trivial group homomorphism. We call it identity on G. And guess what? F composed identity on G, I think that's G prime, is equal to F, which is equal to F composed identity on G. Okay, so it's associative. Group homomorphism composition is associative. Group composition also has an identity. That's a circle. Okay, and we have that. I'd like to do one example of, two examples of a group homomorphism. It's the last thing in the book. Last two, it's on page 31. I'm sorry, the pictures were on 30, so this is on page 31. Okay, so I want to talk about a nice group, a group that you've seen since 6th grade. It's the real numbers. Okay, the operation is addition. The unit is 0, so x plus 0 is equal to x for any real number. Okay, and the inverse is really minus. Let's just make sure we understand what that means. X plus minus x is equal to 0. Let's do that. X plus 5 plus minus 5 is equal to 0. So that's a nice group. Okay. We'll talk about another group. I'm going to call this R plus. Maybe I'll call it R star. No, I'll call it R plus. This is positive real numbers. Okay, and we can multiply positive real numbers. And there's a unit 1. Let's just make sure. So this is multiplication. So you know what? I'm going to make multiplication as a dot. Okay, because there's too many stars around here. Dot. So I can multiply x times y. Okay, this is a unit, which means x times 1 is equal to x. We know that. Okay, and what is the inverse operation? 1 over x. Okay. I'm sorry. So let's write this as minus 1. Okay, so here's two groups. Okay, this is called the additive group of real numbers. This is called the multiplicative group of positive numbers. Okay, great. Now, let B be a member of R. Can't be 0. Maybe B should be more than 1. I'm not sure. Yeah, shouldn't be 0, that's for sure. Okay, now I have a function from here to here. Okay, and I'm going to write the function like this. Boom. Okay, B is the base of exponentiation. Okay, good. So how does this function work? It takes a number x and it takes it to b of x. Okay, great. Okay, now I want to go talk about those laws of group homomorphisms. So we have as follows: x plus y goes to b of x plus y. That's one thing we could do, but there's another thing we can do also. We can see where x goes, we see where y goes to b of y, okay? And what we want is, let's just remember what that rule was, f of x star y is equal to f of x star prime f of y. Okay, so guess what we want? We want this to equal to b to the x, that's this guy. So find the image of this guy, find the image of this guy, and do the operation here. What's the operation here? Multiplication. So we're taking addition to multiplication. Okay, so that is dot b of y. Okay, now this is a rule that you learned in 8th grade. Exponentiation takes addition to multiplication. Okay, but here's another way of saying it. It's a group homomorphism. Okay, it's a group homomorphism. Okay, but hold on, we're not finished. Because there's another group homomorphism, and it goes this way. And it's called log base b. Okay, now let's see what happens here. So x goes to log base b of x, and y goes to log base b of y. And now, how about x times y? Well, guess what? That's going to go to log base b of x times y, but we want it to be a group homomorphism. What does it mean that it's a group homomorphism? That means you can look at the individual images and see what you get and do the operation here. So this is equal to log base b of x plus log base b of y. So the fact that this is a group homomorphism is nothing more than something you learned probably in 8th grade or 9th grade. So that's very nice. Okay? Okay, so let's summarize a little because it's a long class. Let's summarize a little. You ready? So what did we see? We learned a lot about sets. Okay, we learned a lot about sets, about maps going into sets, maps going out of sets. We learned a lot about those set operations and function operations. What were the function operations? Composition, lifting, and extending. Okay, and then we saw 3 different things: equivalence relations, graphs and graph homomorphisms, groups and group homomorphisms. These 3 things, sets, graphs, and groups, are going to be things that we can learn a lot from when we talk about categories. Okay, so these are structures that we're going to see over and over and over again, and structures that have similar properties to categories. I said before, a category is a souped up graph. Okay, because, well, I'll explain to you why. It's also, you can see a category as a souped up group also. It's a different type of group also. So we're gonna see that. So we're getting used to sets, we're getting used to groups, we're getting used to graphs, and then we're gonna come next lecture is going to be on section 2.1, where I start off just doing the definition of a category and then tens of examples of categories. You're going to see these axioms showing up over and over and over, and it's going to be a fun time. Okay, thank you very much.